So what we're going to go over here is how to interpret graphs of motion, different types of motion. So basically graphs of displacement and velocity and acceleration, and what kind of information we can get from these. So if we were to take and do a graph of displacement on our vertical axis as our dependent variable, so displacement, and then do time on our horizontal axis, our independent variable, and we were to get some sort of graph on here. It can be whatever shape we want, but we'll do some kind of like straight or straightish line shape graph, something like that. Then there's some information that we can actually get from this this graph. And so if we were just reading this, we'd go along and read as time increases, then this just tells us what happens to this person's position relative to where they were, and we go from there. So some of the things we can get from this, or the first major thing we can read from this, is the slope of the graph. And when you look at some sort of line segment, so let's say we're looking at this part, pretend that I drew that and it was actually pretty straight. Look at this section here. It has an overall slope to it. And if we go to calculate slope, if you remember, slope is just rise over run, or change in your vertical over change in your horizontal. So it would be the vertical change, that distance, versus your horizontal change, right? And if we divide those by each other, the vertical change would, if you came straight across, it would be a certain change in the position, a delta x, and the horizontal change would be a certain amount of time, a delta t, a change in time. And if you remember back how we defined velocity, that change in position here over change in time is velocity, which means that if we were to do this, that would tell us what our velocity was during this segment of the graph. If we then wanted to see, how fast was it going over here where the slope changed a bit, you pick a couple points along that straight line segment and do the same sort of thing. Find the change in x and the change in time, and you would get a slope for it. This is not the only kind of graph we can do. We can also do a velocity versus time graph, where we put our velocity on the vertical axis and time on the horizontal axis, and we would have some sort of graph that goes along there. And again, we could take a slope on here, and our slope, we could do line segment, say like from here to here, and we'd have some sort of change in time and some sort of change in velocity, and our slope here would then be a change in the velocity, that's our rise, over the change in time, that's the run. And if you remember back to how we defined acceleration, you would see that it was the rate of change of velocity, which is the change in velocity over the change in time. And so this would give us the acceleration during that part from here to here, that part of the straight line part, it would be that. And if we tried to do it here, it would be something else. If you notice at this part, it would have a negative slope, which would give us a negative acceleration. And so you can have the positives and the negatives as well. The third kind of graph we could do to go along with this would be an acceleration versus time graph. And for acceleration versus time, most of what we will do will have, oops, that's not very good. That was supposed to be perfectly horizontal. We'll have a horizontal, try that again. We'll have a nice horizontal line like that, because pretty much everything we're going to do is constant acceleration, which means there won't be any change in it as time goes on and on. You just stay at one constant acceleration. So if you were to take the slope of this here, the slope, you could again do rise over run, but the rise, the change in 8, would just be 0 over whatever amount of time you wanted to look at. And so 0 divided by however much time you look at, it's just going to be 0 here. A 0 acceleration, or rate of change of acceleration. So as far as this level goes, we don't have to worry about when there's a changing acceleration. We're not going to really be taking slopes of that because everything we're going to do constant acceleration. There is one more thing you can do with these graphs other than just looking at slope of them, and that's to look at the area underneath the graph. So if I were to take and draw this straight down, draw that straight down, and just look at this area underneath this graph here, well, turns out if we do the area under this graph, it's not going to tell us too much. Okay, this one isn't really going to tell us anything, but just as you look at it, we have a rectangle here and a triangle here, and so finding the area of these rectangle triangles is not really too difficult. But you could go in and find those, add those areas together. But if you look at this dimensionally, okay, you look at it dimensionally, the area under this graph is going to have a dimension of, like when we do the area of this square, it's going to be the base times the height, and that would be a unit of time times a distance. So it'd be something like a meter second, which doesn't really have much physical significance for us, a meter second. I'm not even sure what that means. So the area on this one, the area under, kind of really is no help here. It doesn't help us at all. We don't get really any information there from that one. But if we come over here and we do the area underneath this one, so like let's say we did from here to here, we would have a rectangle we could find the area of, and we could have a triangle that we could find the area of, and we would add these two areas up and get the total area underneath the graph from here to here. Well, the area under here would be a velocity times a time, which would be something like a meter per second times a second, which would cancel out and just leave us with meters. So obviously, evidently, this is just some sort of distance that would be left over, and it turns out this would be the displacement. Going off the edge there, but it'd be the displacement that occurred during that time from whatever this would be. We could call this T1 to T2. So we could use this to figure out how much displacement occurred. So if you went into this graph and found an area underneath all the different sections of it, we could actually then recreate this previous graph here and take a velocity versus time graph and turn it into a displacement versus time. And of course, using the slope to get velocity from the displacement versus time graph, we could take the displacement versus time graph, take a bunch of slopes, and rebuild the velocity versus time graph. Similarly, you can come to this acceleration graph, and you can do an area underneath it. This is pretty simple because we're only going to do these straight line accelerations. You do the area underneath it, and you have an acceleration times a time. And an acceleration times a time, this would be a meter per second squared times a second, would give you a meter per second, and it turns out that that is just the case. You get area under this to be acceleration. Okay? So you could take this graph, I'm sorry, not acceleration, velocity. You would get velocity. So you could take an acceleration versus time graph and rebuild a velocity graph. You could go and find all the area underneath and find what the velocity was at different points as time goes on. And if you think about this, if you're accelerating constantly and you look at this, the area, as we keep taking higher and higher times, as we go further and further out, if we keep adding on extra areas, we would add on more and more velocity, and it would be just getting faster and faster and faster. So essentially the way this works is you start with displacement versus time graph. If you take a slope, of that, don't need that. If you take a slope of this, it will move you over to velocity. If you take the slope of velocity, draw an arrow here, it'll move you over to acceleration. And then, once you get to this end, the slope here doesn't really tell you much. It does have a physical significance, it's just not one we're interested in. if that happens, you can come back and you can take the area under and take a step back to velocity. And if you take the area under here, you can take a step back to displacement. So as long as you have really one of these graphs, depending on whether or not you take slopes or areas, you can step back and forth between these, one to the other. Slopes will take you this way, and area unders will take you back. All right? And this kind of stuff is not just true for displacement versus time graphs, it's actually true for a lot of different kinds of graphs. So whenever you are given a graph, especially on a test or something, you need to check and look at what the dimensions would be of the slope. If I took the vertical axis and I divided it by the horizontal axis, what kind of information would that give me? Okay? And check the area underneath. What if I took the vertical axis and I multiplied it by the horizontal axis? What dimension would that be? What kind of information would that be? Because you're almost guaranteed to get a question on a test where it's going to give you some sort of graph you haven't seen before, and you need to check and see what can you do. Can I get something from the area under it, or can I get something from the slope? And then you're going to have to do that. It might be some sort of force graph or some other kind of crazy thing. So be very careful. Every time you get a graph, you ask yourself, what can the slope tell me, and what can the area underneath tell me? Now, there's one last thing that I have to say about finding these areas and these slopes, because all of these, I tried my best to draw these as nice, straight lines. Well, what happens if these are not nice, straight lines? And we'll just do an example of one of them, like velocity versus time. We'll redraw that one. So what happens if we have a velocity versus time? I'm going to make this one bigger here. What happens if we have velocity versus time and it is not a straight line? Say our curve is doing something like this. It's actually curving along like that. And then you were asked to find what the acceleration was at some point. Well, there's no straight lines in here for you to then go along that line and take the slope of it. So what we can do is actually come up with the idea of something called instantaneous velocity, or oh, misspelled that. Oops, my S there. So instantaneous velocity, which we wouldn't get from this graph, or instantaneous acceleration. So oops, I left out a C there. Not doing so great on that today here. So instantaneous velocity or acceleration, and this graph we'll use to get instantaneous acceleration. So if I look at this, what happens is I could say maybe I wanted to know what was the acceleration right at this moment on the graph, right there. Well, I could approximate it. I could pick some point over here, and I could pick some point over here, and I could just draw in a straight line, and I could say, all right, if I take the slope of that, then it's going to be kind of close to what the acceleration is actually at this point. But close is okay, but I could do better. So perhaps what I decide is maybe I'm just going to be a little more careful, and I'm going to pick two closer points now. And I'm going to just draw a straight line between them, and that's going to be even closer to what I want. And then I think, well, I can do better, so I pick even closer points. And it's getting a little messy. You can't really see it there, but I'm going to pick closer and closer points. And if I want to keep going, what I can do, if I zoom in on that little spot, let's say I zoom in on this little portion of the curve here, we're going to make it bigger over here. All right? If I'm looking at that portion of the curve where it's just curving like this right through there, and I just keep getting closer and closer, what I'm essentially going to do is I'm going to get down, I'm interested in the slope at this point, and I'm going to get down and I'm going to get just 2 points. The smallest things that you possibly can that are just literally right next to each other, so close that are practically on top of each other, there's no distance between them. And then what I'm going to do is I'm going to take the slope between those 2 points. And what this basically gives me, if I can draw this, is the slope of the line tangent to that point. And that tangent line at that point whether this be a velocity graph or a displacement graph, the slope of that tangent would tell me what the instantaneous velocity or the instantaneous acceleration was at that exact moment. So in practice, you don't have to necessarily go through and zoom way in and do this. You just have to come along, pick a spot on the graph, like say right here, and you draw in, you put your ruler right on it, and you draw in this tangent line. It goes and just touches the graph at that one single point, and then goes off. And then take the slope of that line, do the rise over run of that tangent line, and you would get the instantaneous acceleration, in this case, of this graph. If I changed this to a position displacement versus time graph, or position versus time graph, then this instantaneous velocity would be this slope here of the tangent line would be instantaneous velocity. Of course, in this case, it's instantaneous acceleration. But anywhere you really go, you just draw in that tangent line, and so right there, that would be the acceleration. You could come over here, and oh, there's the acceleration at that point. And as you can see, even just by looking at this, the way I drew this, it would have a very high acceleration at the beginning, then the slope of tangent lines would kind of curve over, and then you'd get a point like this where the slope of the tangent line was 0 and there was no acceleration, and then the acceleration would go a little negative before going back to 0 and then starting to curve back up. And everywhere along here, you just go in and you draw these tangent lines in and get what the acceleration was instantaneously at that point. All right, and that's all.